The universe is about to perform a magic trick, and we are the audience watching from the worst possible seats. In less than a day, the third interstellar object ever discovered will not explode, not fade, but vanish. It will slip directly behind the Sun, into a region where no telescope on Earth can follow. Astronomers call this a solar conjunction, a clinical term for a profoundly dramatic event. I call it the universe closing its curtain. For the first time in history, an interstellar visitor will reach the most energetic, volatile, and scientifically critical moment of its entire journey, completely hidden from our view. This object, designated 3I Atlas, discovered on July 1, 2025, by the same network that watches for asteroids that might have our name on them, is not like the ones that came before. Oumuamua, that strange cigar-shaped first visitor, and Comet Borisov, the more familiar-looking second, both remained visible during their closest approaches to the Sun. We could watch them, measure them, and point every instrument at them. Atlas offers no such courtesy. It reaches its perihelion, its point of maximum speed, solar heating, and tidal force, on October 29th, just 8 days after it disappears behind the Sun's overwhelming glare on October 21st. This isn't just another astronomical event. It is an unprecedented blackout at the worst possible moment. The climax of the play is happening behind the curtain, and we are left sitting in the audience, waiting in silence, forced to wonder what spectacular or terrifying scene we are missing. This is the story of that silence, of the questions it forces us to ask, and of the possibility that our understanding of what moves between the stars is about to be shattered. As we begin this journey together, I want you to be a part of this global vigil. Where are you watching from right now, and what time is it on your clock? Drop a comment below and let me know. And if you want to follow every twist and turn of this mystery as it unfolds, make sure to subscribe to this channel. The vanishing point is approaching, and we are about to go dark on one of the most extraordinary visitors we have ever received. The countdown has entered its final hours, and across the world, from the great professional observatories on mountaintops to the dedicated amateurs in their backyards, a frantic global scramble is underway to capture the last possible glimpses. The final photons of data before the cosmic curtain falls. Every spectrum, every astrometric measurement, every final image is a precious piece of the puzzle, a snapshot that will have to sustain our curiosity and our science through the long weeks of blindness that lie ahead. We are about to lose our connection to an object that has traveled for millions of years through the interstellar void, only to have its most defining moment occur in perfect secrecy. The tension is not just scientific, it is narrative. We are being denied the story's climax, and the human mind abhors such a vacuum. It is in that vacuum that wonder, speculation, and a profound sense of cosmic anticipation will grow. To fully grasp the magnitude of what we are losing, we must dissect the silence window with brutal technical clarity. When astronomers state that we will be blind to 3I Atlas for several weeks, this is not an exaggeration for effect. It is a literal declaration of our observational limitations imposed by the laws of physics and the fragility of our technology. The Sun is an unforgiving adversary to astronomy. Its overwhelming glare doesn't just wash out faint objects, it poses a genuine threat of destruction to the sensitive optics of our most powerful telescopes. To point an instrument like the Hubble or the Vera C. Rubin Observatory anywhere near the Sun is to risk melting its multi-million-dollar components, turning a tool of discovery into a molten piece of scrap metal. Therefore, we do not look. We cannot look. This self-imposed blindness, this solar conjunction, strips away the foundational tools of modern astrophysics for the duration of Atlas's hidden passage. The first and most profound loss is spectroscopy, the art and science of cosmic chemistry. As sunlight passes through or reflects off the coma and tail of a comet, it carries with it a unique fingerprint, a barcode of absorption and emission lines that reveals the precise atomic and molecular composition of the gases being boiled off the nucleus. This is how we know a comet contains water ice, carbon dioxide, cyanogen, ammonia, and complex organic molecules. It tells us not just what the object is made of, but how active it is, and by extension, something about the conditions of its birth in a distant star system. Without spectroscopy during this critical perihelion period, we are utterly blind to Atlas's chemical evolution. If it were to suddenly begin venting a strange isotope ratio, or a molecule we've never seen in a comet before, we would remain in ignorance. Second, we lose the precise, painstaking work of astrometry. the measurement of the object's exact position and velocity over time. Every observation of Atlas since its discovery in July has allowed astronomers to refine its hyperbolic trajectory, creating a predictive model of its path through our solar system. However, if the object experiences any non-gravitational forces during the conjunction, a sudden jet of outgassing acting as a thruster, or something else, its post-conjunction trajectory will not match the pre-conjunction prediction. We will be left with a before and after picture, forced to play a frustrating game of celestial detective, trying to deduce what unseen event in the middle caused the discrepancy. The longer the observational gap, the greater the uncertainty grows. And for an object as inherently anomalous as an interstellar visitor, this uncertainty is deeply uncomfortable for scientists who rely on continuous data to build confident models. Finally, and perhaps most viscerally, we lose all imaging capability. We will not see if Atlas undergoes a dramatic physical transformation. Comets are notoriously fragile. The intense heat and tidal forces at perihelion can cause them to crack, shed massive fragments, or even disintegrate entirely. We have witnessed solar system comets like Shoemaker-Levy 9 or Comet Ison be torn apart by the sun's gravity. If Atlas fragments during its hidden perihelion, we will not witness the event itself. We will only see the aftermath, a diffuse cloud of debris, or a string of smaller objects where once there was a single nucleus, and we will be left to guess at the precise moment and mechanism of its demise. This is the core of the problem. Perihelion is the moment of maximum drama. When the object is moving at over 100,000 kilometers per hour, solar heating is at its peak, and internal stresses are most likely to cause a spectacular outburst or a catastrophic breakup. It is the moment when comets become most interesting, most active, and most unpredictable. And it is the exact moment we are forced to turn our backs, leaving the most scientifically rich chapter of Atlas's story unwritten and unread. The peculiarities of 3I Atlas are not limited to its inconvenient timing. They are deeply encoded in the very geometry of its path through our solar system, a trajectory that presents a series of orbital puzzles begging for an explanation. When an object originates from the interstellar void, ejected from some distant star system millions of years ago, we expect its arrival direction to be random. The solar system is a tiny island in a three-dimensional ocean, and visitors from other shores should, statistically, approach from any angle, steeply from above the ecliptic plane, from below it, or from any point on the celestial sphere. There is no reason for an outsider to respect the flat, pancake-like plane in which our planets orbit, a structure that formed from a rotating disk of gas and dust 4.6 billion years ago. Yet Atlas did exactly that. It entered our solar system aligned with an astonishing precision, tilted a mere 5 degrees from the ecliptic plane. This is profoundly unusual. It's like a stranger walking into a crowded building and immediately, perfectly merging with the flow of employees who have worked there for decades. The simplest explanation is coincidence. Statistics allow for outliers, and Atlas could simply be that 1 in 1,000 object that, by pure chance, arrived on this particular trajectory. But science grows wary when coincidences begin to pile up. This neat arrival angle is the first piece of a larger puzzle. When astronomers attempt to backtrace Atlas's path to find its point of origin, they run into a wall. The mathematics point generally toward the constellation Sagittarius, in the direction of the crowded galactic center. But no specific parent star emerges from the calculations. It is as if the object emerged from a statistical fog, its path scrambled over millions of years by the complex gravitational influences of passing stars and dark matter clouds, rendering its origin untraceable. This stands in contrast to Comet Borisov, whose path could be loosely traced back to a region of active star formation. Atlas is an orphan with no identifiable home. Compounding this mystery are subtle anomalies in its velocity. Precise astrometric measurements collected since July suggest that Atlas is moving very slightly faster, or on a slightly different path, than what would be predicted by gravity alone. For solar system comets, this is a common and well-understood phenomenon caused by outgassing, the asymmetric vaporization of ices that acts like a tiny natural rocket engine. But with Atlas, we have not had enough observation time to confirm this is the cause. The deviations are subtle, lingering at the edge of measurement error, but they are there. So, we have an object that is unusually aligned with our solar system's plane, has no clear origin, and exhibits potential velocity anomalies, all while on a course that takes it behind the sun at the most critical moment of its journey. This collection of facts does not, in itself, prove anything other than that Atlas is a fascinating and complex natural object, but it does open a door, however slightly, to a more profound line of inquiry. When multiple low-probability factors align so perfectly, it forces us to ask whether we are looking at a series of random cosmic dice rolls, or if we are seeing the faint, indirect signature of something else entirely, a trajectory that has been optimized, rather than one that simply happened. As 3i Atlas prepares for its covert solar rendezvous, the night sky itself seems to be engaging in an act of cosmic misdirection, offering a brilliant spectacle that threatens to draw the public's gaze away from the hidden drama. In a staggering juxtaposition of timing, the heavens are putting on a show centered around October 20th and 21st, featuring two bright comets that are reaching their peak visibility for observers in the northern hemisphere. This is the sky's counterpoint, a vivid display that stands in stark contrast to Atlas's stealthy disappearance. The first of these, Comet C 2025A6, known as Lemmon, was discovered on January 3, 2025, by the Mount Lemmon survey in Arizona. It has been steadily brightening as it approaches Earth. And on October 21st, the very day Atlas enters solar conjunction, Lemmon makes its closest approach to our planet at a distance of about 90 million kilometers. Under dark, clear skies away from city lights, it should be visible to the naked eye as a faint greenish smudge. Its characteristic color is a product of diatomic carbon molecules in its coma being excited by sunlight, a classic and beautiful phenomenon of cometary science. To find it, one would look toward the northwest horizon after sunset, where it will hang low, perhaps 15 to 20 degrees above the horizon. The second act in this celestial double feature is Comet C 2025 R2, nicknamed SWAN, discovered more recently on September 10, 2025, by the SWAN instrument aboard the SOHO spacecraft. SWAN specializes in detecting the hydrogen Lyman alpha glow of comets, often finding them before they are bright enough for ground-based surveys. It reaches its own close approach to Earth around the same dates, coming within 40 to 50 million kilometers. It will be positioned low in the southwestern sky after sunset, another target for twilight observers, though its visibility is less certain and will likely require binoculars or a small telescope. Adding to this cosmic traffic jam is the annual Orionid meteor shower, which also peaks around October 20th, 21st. The Orionids are debris left behind by the most famous of all comets, Halley's Comet, and as Earth plows through this stream of dust particles, they vaporize in our atmosphere at 70 kilometers per second, creating swift, bright shooting stars that radiate from the constellation Orion. So, on the very nights that the interstellar visitor Atlas vanishes from view, any person who steps outside can potentially witness two green comets and a meteor shower. The thematic resonance is powerful and unavoidable. Comets Lemmon and SWAN are solar system natives, likely originating from the Oort cloud, and now making one of their periodic, predictable returns to the inner solar system. They are part of our family, their journeys governed by the sun's gravity, and they are putting on a visible, accessible, and shared display for all of humanity. Atlas, in stark contrast, is the ultimate outsider. It came from another star, it is only passing through, and it will never return. And at the moment its solar system cousins are putting on their finest show, Atlas is performing its most critical act in total secrecy. This creates a narrative schism. The obvious versus the hidden, the spectacle versus the secret, the known versus the profoundly unknown. One could view the dual comet display as a magnificent distraction, a cosmic sleight of hand that ensures the world's amateur astronomers and social media feeds are filled with images of Lemmon and SWAN, while the truly groundbreaking story of the interstellar object unfolds unseen, behind the impenetrable glare of the sun. It is a coincidence, surely, but it is a coincidence that feels laden with meaning, forcing us to question what we are being shown and what we are being encouraged to ignore. The final countdown has now begun, compressing the global astronomical response into a window of less than 24 hours, a period of intense, focused activity that represents our last chance to gather data before the informational blackout descends. This is the decision window, the final opportunity to point every available instrument at 3i Atlas and extract every possible photon of information it has to offer. Across the world, from the high-altitude deserts of Chile to the volcanic peaks of Hawaii, major observatories are executing emergency override protocols, utilizing directors' discretionary time, precious, flexible slots reserved for time-sensitive, once-in-a-lifetime events, to train their massive mirrors on the fading interstellar visitor. The process is a testament to the flexibility and passion of the scientific community. While telescope time is normally booked months in advance through a competitive proposal system, the unprecedented nature of an interstellar object reaching perihelion during conjunction justifies breaking the routine. The goal is to secure final, high-resolution spectra to lock in its baseline composition, capture last light images to document its pre-conjunction structure and brightness, and collect a final burst of ultra-precise astrometric data to refine its trajectory to the highest possible degree. Every second of telescope time is now invaluable, and the data flowing in will become the bedrock upon which all post-conjunction analysis will be built. Simultaneously, the global network of amateur astronomers is demonstrating its critical role in modern science. Armed with sophisticated backyard telescopes, CCD cameras, and specialized software, these dedicated hobbyists are contributing vital observations. They provide additional data points for astrometry, helping to narrow the trajectory, and perform photometry, measuring the object's brightness, which can reveal subtle changes in activity. This distributed, resilient network of observers operates outside the rigid constraints of professional institutions, allowing for rapid mobilization and data sharing. Their collective effort represents citizen science at its best, a global community united in the pursuit of understanding a fleeting cosmic phenomenon. However, beneath this organized, data-driven scramble, an undercurrent of rumor and speculation is flowing through the astronomical community. Unverified reports, shared in hushed tones at conferences and in private online forums, suggest that preliminary spectroscopic data from Atlas has revealed an unusual chemical composition that has not yet been made public. The specifics are vague. Whispers of anomalously low water content, strange ratios of cyanogen compounds, or unexpected metallic signatures. But the implication is that the object's chemical fingerprint does not neatly match any known population of comets from our own solar system. This data is said to be under embargo, undergoing the slow, meticulous process of peer review before publication. Are these rumors credible? In the world of science, preliminary results are just that, preliminary. They often do not survive rigorous scrutiny and replication, but the very existence of these whispers adds a potent layer of intrigue to the final hours. Composition is the key to origin. If Atlas's spectrum is genuinely anomalous, it would suggest it formed under conditions radically different from those in our solar system. Or, for the wildest of speculators, that it is made of something else entirely. For the individual with access to a moderate-sized telescope, Atlas is still, for these final hours, a tangible target. Though faint, at a magnitude of 13 or 14, far beyond naked eye visibility, it can be captured with an 8-inch aperture telescope, a sensitive camera, and a long exposure. To be the one who captures one of the very last images of this interstellar wanderer before it vanishes is to participate in a moment of historical astronomy, a small but meaningful connection to a mystery that spans the light years. As the hours relentlessly tick down, a palpable psychological shift occurs among those who are closely following the event. The anticipation of discovery is now mixed with a sense of dread for the impending informational void. We are about to sever our direct link to an object that has journeyed across the galaxy. It will continue its voyage, but we will lose all real-time knowledge of its state. It is akin to watching a loved one walk into a long, dark tunnel. You see them enter, and you must wait, powerless, for them to emerge on the other side, hoping against hope that they will be the same person who went in. To fully appreciate the context of 3I Atlas's arrival, we must zoom out to a galactic scale and consider a provocative, albeit speculative, framework known as the Sagittarius Corridor hypothesis. This idea suggests that the structure of our Milky Way galaxy is not a uniform, random distribution of stars, but may be threaded with preferential pathways, gravitational corridors, that guide the flow of material across vast interstellar distances. The evidence for this is circumstantial, but intriguingly consistent. 3I Atlas itself entered our solar system from the general direction of the constellation Sagittarius. Its predecessor, the first interstellar object Oumuamua, also had a backtraced origin that pointed roughly toward the galactic plane in that same general direction. Even the most famous anomaly in SETI history, the WOW signal detected in 1977, originated from the vicinity of the constellation Chi Sagittari. Sagittarius is not just any patch of sky. It is the direction of the galactic center, the dense, massive hub of our Milky Way, home to the supermassive black hole Sagittarius A and a swarm of billions of stars. It is, by definition, a target-rich environment, and one where we naturally point many of our telescopes. This clustering of anomalous events could therefore be a simple result of selection bias. We find interesting things where we look most often. However, the Sagittarius corridor hypothesis proposes a more physical explanation. The concept, explored in fringe areas of astrophysics, posits that the combined gravitational influence of the galaxy's structure, the pull of spiral arms, the gravity of billions of stars, the unseen hand of dark matter, can warp space-time in such a way as to create regions of slightly lower gravitational potential, akin to valleys or riverbeds on a continental scale. Objects traveling through the galaxy over millions of years would naturally tend to drift into these corridors, following paths of least resistance. They would be the interstellar equivalents of trade winds or ocean currents. If such corridors exist, they could explain why multiple interstellar objects, despite their random ejection processes, might appear to arrive from a similar general direction. This hypothesis takes on an entirely different dimension when viewed through the lens of potential intelligence. If an advanced civilization were to embark on interstellar exploration, it would be logical and energy efficient to use these pre-existing gravitational highways. A probe would not need to expend colossal amounts of energy to travel in an arbitrary direction. It would simply enter the local galactic current and let it carry it through star-rich regions, maximizing the probability of encountering interesting systems like our own. From this perspective, an engineered object and a natural one would share a similar trajectory. The artificial probe would be a stowaway on a natural gravitational flow, its path perfectly camouflaged among the driftwood of the galaxy. This is not proof of anything, but it provides a theoretical framework that makes the idea of directed travel less fantastical. It reframes the question from, why would a probe come from that direction, to, if a probe were coming, that is the direction it would most likely come from. The wow signal remains a haunting piece of this puzzle. A strong, narrowband radio signal that appeared once and was never detected again. Its origin in Sagittarius links it, however tenuously, to this concept of a busy galactic thoroughfare. While drawing connections between a 48-year-old radio burst and a physical object detected today is a classic example of potential pattern-matching fallacy, the directional coincidence is a data point that cannot be entirely ignored. The Sagittarius corridor hypothesis remains exactly that, a hypothesis. It is not a proven theory of galactic dynamics, but an intriguing idea that deserves further investigation as we discover more interstellar objects. It suggests a universe that is less a random scattering of stars and more a structured, flowing system with well-traveled routes. And if that is the case, then 3i Atlas may not be a lone, lost wanderer, but a traveler on an ancient, cosmic highway, and its passage through our system, hidden or not, is a routine event in a galaxy that is far more connected and dynamic than we have ever imagined. As the clock ticks down on our ability to observe 3i Atlas, an uncomfortable but necessary conversation is taking place in the background of the scientific and public discourse, the debate over data suppression. In the corners of the internet, among conspiracy theorists and serious amateur astronomers alike, a serious question is being raised: is all the data being collected on this anomalous object being shared freely and immediately, or are certain findings being delayed, classified, or withheld by government agencies or scientific institutions? To address this, we must first understand the normal and generally transparent workflow of astronomy. The field operates on a principle of peer review and public data archiving. Observations from major telescopes are eventually published in scientific journals, and the underlying data is often deposited in public archives so that other researchers can verify the results and conduct their own analyses. This openness is the bedrock of the scientific method. However, there are legitimate and standard exceptions to immediate release. The most common is the proprietary period, when a team of astronomers invests years in designing an instrument and writing a successful proposal for telescope time. They are typically granted a period of exclusive access to the data, usually 6 to 12 months. This allows them the first right to analyze the data and publish the groundbreaking results, protecting their intellectual investment. From the outside, this can look like suppression, but it is a standard practice meant to incentivize and reward the immense effort involved in cutting-edge research. Beyond this, there are genuine national security considerations. Some space-based assets, particularly those operated by military organizations, detect objects that governments deem sensitive, debris from classified missions, spy satellites, or even near-Earth objects that might pose an impact risk before a mitigation strategy is publicly formulated. In these cases, data can be legitimately classified to prevent public panic or to protect state secrets. When it comes to Atlas, the rumors of withheld data specifically involve spectroscopic results. The official reasoning, if these rumors are true, would be the standard scientific caution. The data is preliminary, potentially noisy, and requires confirmation and peer review before a public announcement is made. The scientific community has been burned before by premature announcements of extraordinary claims, cold fusion, faster-than-light neutrinos, that later had to be retracted, damaging public trust. The desire to be certain before speaking is a responsible one. However, this inherent caution collides with the unique circumstances of the Atlas conjunction. The delay created by the peer review process, which can take many months, means that any potentially explosive findings about Atlas's composition would only be published long after the object has re-emerged from behind the sun. During that gap of official silence, speculation will run rampant. People will assume the worst, that a cover-up is in progress. The question then becomes, are there reasons beyond scientific caution for suppressing data? One could theorize that if Atlas were displaying clear, unambiguous techno-signatures, signs of artificial origin, the societal implications would be so profound that governments might want to control the release of that information. Protocols for announcing the discovery of extraterrestrial intelligence do exist, developed by organizations like the International Academy of Astronautics, and they emphasize cautious, coordinated, and verified announcements, not rushed disclosures driven by social media. On the other hand, astronomy is a global endeavor. Atlas is being observed by telescopes in dozens of countries, not to mention by a distributed network of amateur astronomers. The idea that a finding as monumental as evidence of an artificial object could be suppressed across this entire decentralized network is nearly implausible. Leaks would be inevitable. The most likely reality is a mix of standard scientific process and heightened public interest. Some data is delayed for proprietary reasons, some findings are undergoing necessary verification, and some rumors are simply that, unsubstantiated speculation. But the conjunction creates a perfect storm for suspicion. The object is physically hidden, and if information about it also becomes hidden, the void of knowledge becomes a vacuum filled with doubt and conspiracy. This makes the role of independent, amateur observers more crucial than ever. They are a check on institutional control, capable of collecting and sharing data outside of official channels. If something dramatic happens to Atlas when it re-emerges, they will be the first to see it and the first to tell the world. The data suppression debate, therefore, is less about proving a specific conspiracy and more about acknowledging that the flow of information in science is not always instantaneous or perfectly transparent. In the case of an object as mysterious as Atlas, that gap between observation and understanding becomes a part of the story itself, a reminder that what we don't know and what we aren't told can be just as powerful as what we see with our own eyes. No discussion of interstellar objects and the possibility of artificial origins can proceed without addressing the central, controversial figure who has come to define the debate, Professor Avi Loeb of Harvard University. The Loeb factor has become an inescapable element of the three-eye Atlas narrative, injecting a provocative, philosophical tension into what would otherwise be a purely scientific investigation. So, who is Avi Loeb, and why does his perspective matter so profoundly? Loeb is not a fringe character. He is a heavyweight in the world of astrophysics. A former chair of Harvard's astronomy department, he has published hundreds of peer-reviewed papers on black holes, cosmology, and high-energy astrophysics. His credentials are impeccable, which is precisely what makes his foray into the study of interstellar objects so disruptive and difficult for the mainstream astronomical community to dismiss. Loeb first captured global attention with his analysis of Oumuamua. He pointed out its strange properties, its extreme elongation, its tumbling motion, and most importantly, a small but measurable acceleration that could not be explained by gravity alone. While the majority of astronomers attributed this to outgassing, even though no visible coma or tail was detected, Loeb proposed an alternative hypothesis that Oumuamua could be a light sail, a thin, reflective piece of advanced technology pushed by the radiation pressure of the sun. He was careful not to claim it definitely was artificial, but rather that the possibility should be seriously considered and investigated not ridiculed and dismissed. His mantra became, "Extraordinary claims require extraordinary evidence, but extraordinary dismissal also requires extraordinary justification." Now, Loeb has turned his attention to Atlas. In preprint articles and public statements, he has highlighted the same series of unusual coincidences we have outlined. The precise ecliptic alignment, the trajectory that passes near multiple planets while hidden, and the too-perfect timing of conjunction and perihelion, creating a window of maximum energy and maximum privacy. He does not claim Atlas is an alien probe. He states, unequivocally, that it is an extraordinary object that deserves our fullest attention, and that the question of coincidence versus design is a legitimate and necessary one to ask. His critics, who are numerous and vocal within the astronomy community, argue that this approach is sensationalistic and ultimately counterproductive. They contend that by even raising the artificial possibility, Loeb lends credibility to unsupported speculation, conflates unusual with artificial, and risks leading the public to believe that astronomers are seriously considering aliens when in their view they are not. They point to the immense prior probability that any given interstellar object is natural, the reputational damage from past false alarms like the face on Mars, and the concern that focusing on long-shot artificial explanations diverts limited time and resources from the solid, natural science that can be learned from studying Atlas as a comet. Loeb's counter-argument is fundamentally philosophical. He asserts that science advances by exploring all possibilities, especially the uncomfortable ones, and that the burden of proof should not fall solely on the proponents of novel ideas, but also on those who defend the conventional wisdom. If natural explanations for Atlas's strange trajectory and timing seem strained, if they require invoking multiple independent low-probability coincidences, then it is scientifically valid to consider whether an engineered explanation provides a more parsimonious fit to the data. To this end, Loeb founded the Galileo Project, an initiative dedicated to systematically searching the skies for physical artifacts of extraterrestrial technological civilizations. Atlas is precisely the kind of object the Galileo Project would investigate, not because it is proven to be artificial, but because it is sufficiently anomalous to warrant rigorous, unbiased scrutiny. The tension here is fundamental to the progress of science itself. Is it better to follow the data wherever it may lead, even into territories that challenge our paradigms and risk professional ridicule? Or is it wiser to apply Occam's razor with ruthless efficiency, always favoring the simplest natural explanation until the evidence for something else becomes overwhelming and undeniable? Both approaches have their merits and their historical victories. For the story of Atlas, the Loeb factor ensures that the artificial origin hypothesis will remain a part of the public and scientific conversation. It means that when Atlas re-emerges from behind the sun, people will be watching with a dual perspective, looking for the expected natural cometary activity, but also, and perhaps more intently, for any sign, a change in trajectory, an unexpected fragmentation pattern, a burst of radio emission that does not fit the standard cometary playbook. Loeb has set the stage for a level of scrutiny that this object would not otherwise receive. Whether one agrees with his methods or not, his involvement guarantees that we will not look away. And in science, that persistent, questioning attention is often the precursor to discovery. To understand why the timing of 3I Atlas's perihelion is so critically significant from an engineering perspective, we must delve into the fundamental principles of orbital mechanics, specifically a concept known as the Oberth effect. This principle explains precisely why performing a maneuver at high speed is exponentially more efficient, and it is the key to unlocking the energy puzzle at the heart of Atlas's hidden passage. Named after the pioneering rocket scientist Hermann Oberth, the effect is a consequence of the physics of kinetic energy. Kinetic energy is calculated as 1/2 of an object's mass multiplied by its velocity squared, ke hag 1 2m v2. That squared term is what makes all the difference. If a rocket engine provides a fixed amount of thrust, a change in velocity, or dv, the resulting change in kinetic energy is far greater if that thrust is applied when the vehicle is already moving at a high velocity. In simple terms, you get more bang for your buck when you're going fast. For an object falling deep into the sun's gravity well, its velocity reaches a maximum at perihelion, the point of closest approach. For Atlas, this occurs on October 29th. At that moment, it will be moving at a tremendous speed, and any small impulse applied then, whether from a natural jet of gas or an engineered thruster, would produce a disproportionately large change in its orbital energy and trajectory. This is not theoretical. It is a standard technique used by spacecraft engineers for gravity assists and orbital adjustments. NASA's Voyager probes used it to slingshot around the outer planets. And every mission to the outer solar system leverages this effect. Now layer the Oberth effect onto the fact of solar conjunction. Atlas reaches this maximum energy perihelion just 8 days after it becomes unobservable from Earth. This creates a window where an object could execute a highly efficient trajectory-altering maneuver with complete privacy. If you were designing an interstellar probe and wanted to change course, shed a smaller probe, or execute any significant action without being watched, you could not script a more perfect scenario. Maximum available energy from the sun's gravity coinciding with maximum invisibility from the planet you are passing. Of course, natural processes also release energy at perihelion. This is the standard and most likely explanation for anything unusual we might infer later. As a comet heats up, subsurface ices vaporize, pressure builds, and jets of gas and dust erupt from the nucleus. This outgassing can act like a natural, if unpredictable, rocket engine, altering the comet's path in measurable ways. We see this with comets all the time. A comet experiencing a strong outburst at perihelion is entirely normal. A comet breaking apart due to thermal stress or tidal forces is also normal. The difference between a natural and an artificial event would lie in the specifics, the magnitude, the direction, and the precision of the energy release. A natural outgassing event is chaotic and asymmetric. A deliberate burn would be controlled and specific, resulting in a clean, precise change in velocity that would be distinguishable from noise, if we could observe it. And that is the crux of the issue. The Oberth effect makes perihelion the most likely time for any kind of significant activity, natural or artificial. The conjunction ensures we cannot observe that activity. We are left in a position of profound ambiguity. We will only be able to see the before and after states of Atlas. If its trajectory has changed when it re-emerges, we will have to deduce the cause from the effect. Was it a violent natural jetting event, or was it a controlled engineered maneuver? The available energy makes both possible. Our lack of observation makes them indistinguishable. This energy puzzle remains the most tantalizing and frustrating aspect of the entire event. The object is now accelerating on its final plunge toward the sun, gathering speed and energy with every passing hour. In a matter of days, it will hit that peak velocity, that moment of supreme energetic potential, and whatever it is capable of doing, whether it is a simple chunk of ice succumbing to solar fire or a sophisticated piece of technology executing its primary mission, will happen in the one place we cannot see, at the one time we cannot watch. The universe has provided the perfect stage for a secret, and we are locked out of the theater. Stepping back from the intricate details of orbital mechanics and spectroscopic analysis, we are faced with the overarching, synthesizing question that has lingered since Atlas was first identified. Are we witnessing a series of breathtaking cosmic coincidences, or is this a form of choreography? How many unusual factors can we stack together before the explanation of pure chance becomes statistically implausible and the notion of design becomes a more reasonable, or at least considerable, alternative? Let us tally the anomalies. First, the trajectory. Atlas entered the solar system aligned within about 5 degrees of the ecliptic plane. Given the three-dimensional nature of space, the probability of a random interstellar object being so well aligned is low. Let us generously estimate it at 10%. Second, the timing. The object reaches its perihelion, the moment of peak energy and activity, just 8 days after entering solar conjunction, ensuring this climax occurs while we are blind. For interstellar objects, we have no statistics, but for solar system comets, this is a rare occurrence, perhaps a 2% probability. Third, the direction. Atlas came from the direction of Sagittarius, which covers roughly 5% of the sky. Fourth, the planetary encounters. While hidden, its trajectory takes it within observational range of Mars, Venus, and Jupiter, not a close flyby, but a positioning that could be advantageous for a probe. Let's assign a 10% probability to a random trajectory having this characteristic. If we treat these as independent events, multiplying these probabilities, 0.1, 0.02, 0.05, 0.1, gives us a combined probability of 0.0 g1, or 1 in 100,000. This is not impossible. Unlikely events do happen, but it is highly improbable. Now, add in the velocity anomalies, the rumoured spectroscopic oddities, and the fact that all of this is happening during a period of heightened solar activity and a dual comet display in our night sky. Each of these additional factors is explainable on its own, but collectively, they form a pattern that becomes harder and harder to dismiss as mere noise. The naturalist position, held by the majority of astronomers, is that we are simply seeing that 1 in 100,000 outlier. The universe is vast, and with enough objects and enough time, every possible combination of rare events will eventually occur. Atlas, they argue, is our number coming up in the cosmic lottery. It is a natural interstellar comet with an unfortunate, for us, orbit, and nothing more. Invoking aliens is an unnecessary complication that violates the principle of parsimony. The choreography position, while far from proven, argues that the alignment is too specific, too convenient. It suggests that repeatedly invoking chance for each individual strange factor eventually becomes a less elegant explanation than considering the possibility of intent. If something looks designed, moves as if designed, and appears at a time optimal for unobserved operation, then perhaps it is designed. This is not a proof, but an argument for investigation. This debate has a deep philosophical dimension, explored in science fiction from Carl Sagan's Contact to Arthur C. Clarke's Rendezvous with Rama. It touches on the idea that advanced intelligence might not communicate via radio waves, but via physical artifacts, probes that carry information across the millennia, a galactic messaging network made of objects, not signals. Our own Voyager probes are primitive examples of this very concept. They are physical messages in bottles cast into the cosmic ocean. If another civilization were doing the same, we would expect to find objects on unusual trajectories with strange properties that hint at a purpose beyond geology. The burden of proof for such an extraordinary claim remains immense. Yet the tension is real. The conjunction window is about to close, locking the answer away from us. When Atlas re-emerges, we will look for clues, for any deviation from the natural comet script that might tip the scales toward one interpretation or the other. But the answer might remain forever ambiguous, a cosmic Rorschach test that reveals more about our own hopes, fears, and assumptions than about the true nature of the object itself. Coincidence or choreography? The trajectory may already hold the answer, written in the silent language of motion and gravity. We just have to wait for the universe to let us read it. As we wait for 3i Atlas to complete its hidden passage and re-emerge from behind the sun, it is crucial to recognize that our very framework for searching for intelligence beyond Earth may be fundamentally outdated, a point starkly highlighted by a parallel technological breakthrough occurring here on Earth in October 2025. Humanity is on the cusp of deploying operational quantum communication networks, with both the European Space Agency and Chinese space programs reporting successful satellite-based quantum entanglement experiments across continental distances. This is no longer a laboratory curiosity. It is the dawn of a new era of perfectly secure, unhackable communication, leveraging the spooky, instantaneous correlation of entangled particles. While the fundamental laws of physics, specifically the no-communication theorem, prevent faster-than-light information transfer through entanglement alone, these networks create channels where any attempt at interception irrevocably destroys the quantum state, making eavesdropping impossible. This revolution in secure communication has profound and largely unappreciated implications for the search for extraterrestrial intelligence, SETI. For over 70 years, our search has been predicated on one primary assumption, that advanced civilizations will use radio waves, either deliberately in beacons or accidentally as leakage from their own activities. We have pointed our radio telescopes at the sky, listening for the narrowband, patterned signals that nature cannot produce, operating under the belief that radio is a universal, inevitable technological phase. But what if that assumption is catastrophically wrong? Human civilization used prominent radio broadcasts for barely a century before rapidly transitioning to more efficient and secure methods. Fiber optics, directed laser communication, and now quantum networks. If this technological progression is a universal constant, then any civilization merely a few centuries ahead of us would have long since abandoned broadcast radio as a primitive, wasteful, and insecure technology. They would have graduated to tight beam lasers for point-to-point chats, and eventually to a galactic-scale quantum internet for their most critical communications. If such a network exists, we are effectively deaf to it. Our radio telescopes cannot detect quantum-entangled particles used in this way. We don't even know what to look for. It would be akin to a society that has just invented the telegraph trying to detect and decode the global internet. The infrastructure and the very language of the communication are incomprehensible. This directly reframes the mystery of Atlas. If this object is an artificial probe from a civilization possessing technology even a millennium beyond our own, it would be foolish to expect it to broadcast its presence with a simple radio beacon. Its communication, if any, would be with its creators or a network of other probes, using methods we cannot intercept, perhaps via quantum channels during the perihelion conjunction, using the sun's immense energy to power a transmission we are technologically unequipped to even perceive, let alone decode. The silence from Atlas in the radio spectrum, often cited by skeptics as proof of its natural origin, becomes meaningless. Its most telling activities would be occurring in a channel we are not monitoring, during a window when we cannot see it. The quantum breakthroughs of October 2025 serve as a stark reminder of our own technological adolescence and the inherent arrogance of assuming the universe communicates on a frequency we can currently understand. We might be swimming in an ocean of interstellar data traffic, a bustling galactic conversation, and we are sitting on the seabed listening for the equivalent of smoke signals. Atlas, in this context, could be a node in that network, and its secret passage behind the sun might be its scheduled time to check in, upload its collected data on the solar system and its inhabitants, and download its next set of instructions, all while hidden from the prying, primitive eyes of humanity. The challenge of sifting this cosmic haystack for needles is being met not only by new physics, but by new silicon minds. October 2025 is also witnessing a quiet revolution in astronomy driven by advanced artificial intelligence. A new machine learning system, details of which are just emerging, has been applied to decades of archival data from gravitational wave detectors and SETI observations, and it has uncovered 14 previously undetected anomalous events. 14 signals, patterns, or correlations that human analysts, with all their expertise and inherent biases, had consistently overlooked and classified as noise. This is not a minor improvement. It is a paradigm shift. Modern astronomy is drowning in data. Every night, all sky surveys like the soon-to-be operational Vera C. Rubin Observatory will generate terabytes of images, capturing the motions of millions of celestial objects. Human brains are incapable of processing this deluge. We filter, we prioritize, we focus on what our experience and intuition tell us is interesting, and in doing so, we inevitably miss the subtle, the unexpected, the genuinely novel. Machine learning algorithms suffer from no such fatigue or prejudice. They can process millions of data points simultaneously, finding faint correlations and multivariable patterns that are invisible to the human eye. The 14 new detections are proof of concept that our archives are littered with undiscovered treasures. Now apply this powerful new lens to 3i Atlas. As you read this, the final pre-conjunction data is being collected and stored. Human astronomers will analyze it for the obvious features: brightness, gross composition, and trajectory. But what if there are subtler patterns hidden in that data? A faint complex periodicity in its light curve that doesn't match simple rotation. A correlation between specific spectral lines that suggests an unnatural surface composition. A series of tiny trajectory deviations that are individually within the margin of error, but collectively form a statistically significant pattern of course correction. An AI, trained on the behavior of thousands of solar system comets and asteroids, could flag Atlas as profoundly anomalous even before it vanishes, based on data that humans would dismiss as insignificant. The real power of AI, however, will come after the conjunction. When Atlas re-emerges in late November, new data will be collected. The primary human analysis will look for major changes. Has it split in two? Has its brightness dramatically increased? Is its new trajectory wildly different? But an AI can perform a deep comparative analysis that goes far beyond human capabilities. It can detect a 2% change in albedo, suggesting surface modification. It can identify a velocity shift of a few meters per second, the signature of a small but precise impulse. It can find that the ratio of two specific molecules in its coma has changed by a minute but statistically significant amount. This is not science fiction. AI is already revolutionizing fields like exoplanet detection, where it finds planetary transits in Kepler data that humans missed, and in gravitational wave astronomy, where it distinguishes real cosmic events from terrestrial vibrations. For Atlas, this means that the ultimate revelation might not come from a human looking through a telescope, but from a neural network sifting through petabytes of data. It presents a profound philosophical and practical challenge. Do we trust the machine's judgment? If, weeks from now, the human consensus is that Atlas re-emerged looking perfectly normal, but a specialized AI flags it with 99.9% confidence as having undergone a significant non-random change, do we re-investigate? Or do we dismiss it as an algorithmic hallucination? This AI revolution also suggests a haunting possibility for the broader search for intelligence. What if signals from advanced civilizations are not designed for biological cognition? What if they are structured in complex, optimized formats intended for machine interpretation? We might be surrounded by a cacophony of alien transmissions that our pattern-seeking brains simply register as background noise. But that would be instantly obvious and decodable to a sufficiently advanced AI. We may need machines to recognize the artifacts of other machines. As Atlas moves unseen, the algorithms that might ultimately decipher its true nature are being refined, waiting for its return. The most important discovery in human history might not be announced by a triumphant astronomer at a press conference, but by a silent, number-crunching AI that has learned to see what we cannot. Adding another layer of cosmic drama to this already overstuffed October, the sun itself is refusing to be a passive backdrop. The National Oceanic and Atmospheric Administration, NOAA, has issued warnings about the most potent coronal mass ejection cycle since the significant solar storms of 2012. The sun is entering a period of heightened activity as it approaches the peak of its 11-year cycle, and October 2025 sits squarely in this tempestuous phase. Coronal mass ejections, CMEs, are billion-ton eruptions of magnetized plasma launched from the sun's corona at millions of kilometers per hour. When directed at Earth, they can compress our magnetosphere, inducing powerful electrical currents in power grids that risk widespread blackouts, disrupting satellite operations and GPS, and creating spectacular auroras that can be seen at much lower latitudes than usual. The timing, as with everything surrounding the Atlas event, feels unnervingly coincidental. Just as our view of the interstellar visitor is being geometrically blocked by the sun itself is unleashing storms that actively degrade our ability to observe the rest of the sky. Solar storms fill the interplanetary medium with charged particles and radio noise, creating a cacophony that makes it harder for radio telescopes to detect faint signals and can even force space-based observatories to safe their instruments to prevent damage. It is a double blackout, first by geometry, then by electromagnetic interference. This solar activity also directly interacts with objects like Atlas. At its perihelion distance of 1.36 astronomical units, the comet is deep within the sphere of the sun's influence, bathed in the solar wind. A coronal mass ejection passing through its location would deliver a sudden, intense blast of particles and magnetic fields, far more powerful than the steady solar wind. For a natural comet, this could trigger enhanced outgassing, strip material away more violently, or dramatically alter the structure and behavior of its tail. For an object of unknown properties, the effects are entirely unpredictable. Furthermore, the very spacecraft we rely on for peripheral observations during the conjunction are themselves vulnerable. SOHO, Stereo, and the Parker Solar Probe are all designed to study the sun, but an extreme solar storm can still overwhelm their sensors, create noise in their data, or even force them to temporarily shut down non-essential systems to survive. A major CME during the critical perihelion period could therefore compromise the last, best chance for any indirect observations of Atlas's behavior. For those on Earth, the silver lining is the potential for breathtaking auroral displays. A strong CME impact could push the auroral oval far south, allowing people across the northern United States, Europe, and Asia to witness the sky alive with shimmering curtains of green, red, and purple light. It is a beautiful and humbling reminder of our planet's connection to our star. Yet this beauty underscores the irony. While we are treated to a dazzling light show in our own atmosphere, the sun is simultaneously hiding an interstellar mystery and potentially blinding the tools we would use to study it. The sun, in its immense and indifferent power, is both the illuminator and the obfuscator, the bringer of light and the creator of the most profound shadows. The solar storms of October 2025 are a reminder that the universe is not a static stage. It is a dynamic, often violent, and always interactive system, and our attempts to observe it are perpetually at the mercy of its whims. While our primary focus is on the object passing near our Sun, astronomers studying the most massive object in our galactic neighborhood have just reported findings that provide a poignant metaphorical echo to the Atlas story. New observations of Sagittarius A, the supermassive black hole at the center of our galaxy, have revealed complex patterns of X-ray and radio echoes. These are not direct signals, but reflections, light from past flares and feeding events that has traveled for years, even centuries, bouncing off clouds of gas and dust in the black hole's vicinity before finally arriving at our telescopes. This phenomenon, known as a light echo, allows us to study events that happened in the past, to hear the whispers of history reverberating through the caverns of space-time. The study of these echoes is allowing scientists to map the violent environment around Sagittarius A, to understand how matter spirals into the abyss, and to test the limits of Einstein's theory of general relativity in the most extreme gravitational fields possible. The connection to Atlas is not physical, but philosophical. Echoes are information that persists, that arrives delayed and distorted, but carries the imprint of a past event. In a very real sense, an interstellar object like Atlas is itself a kind of echo. It is a physical remnant of an event that occurred millions of years ago, perhaps the gravitational disruption of a distant planetary system, a stellar explosion, or the launch of a probe. It has traveled across the galactic gulf, and its arrival in our solar system is the delayed signal of that ancient event. We are not observing it in real time. We are witnessing an echo. If Atlas is natural, it is an echo of the chaotic processes of star formation and destruction. If it is artificial, it is an echo of a long-gone intelligence, a message in a bottle that has been traveling for eons, its senders potentially extinct, their civilization turned to dust. The object itself is the signal, and its trajectory and composition are the message. The fact that Sagittarius A also lies in the direction of the Sagittarius constellation is another thread in this tapestry of cosmic connections. It reinforces the idea of the galactic center as a gravitational anchor, a place where pathways might originate and where information, in the form of light, matter, and perhaps even probes, might be funneled. The black hole's echoes remind us that the universe is fundamentally historical. Our view is always of the past. When Atlas re-emerges from behind the Sun, we will not be seeing it as it is, but as it was after its perihelion. The light that reaches our telescopes will be an echo of the hidden event. We will be trying to reconstruct what happened during its secret passage from the aftermath, from the delayed signal of its changed state. This is the essential work of astronomy, reading the echoes of the cosmos. Some echoes are loud and clear, like a supernova. Others are faint and subtle, like the whisper of an interstellar comet doing something no comet has ever done before. The black hole studies remind us that no information is ever truly lost. It just travels, reflects, and waits for a listener sophisticated enough to understand its story. The echo of Atlas's passage is now traveling toward us. We must be ready to listen. As we reach the final moments before Three-Eye Atlas slips into its period of maximum secrecy, it is time to turn the mirror upon ourselves. We have spent this narrative scrutinizing an incoming object, dissecting its trajectory, and questioning its nature. But we must now ask the reciprocal and perhaps more unsettling question. If someone or something is watching us, what would they see? And are we, as a species and a civilization, ready to be observed? October 2025 finds humanity at a messy, chaotic, and pivotal transition. We are no longer a species that merely looks at the stars. We are becoming one that operates, builds, and even contemplates conflict in space. Global discussions are intensifying around the ethics of AI-controlled weapons systems in orbit, the management of a dangerously cluttered shell of space debris, and the geopolitical implications of sprawling satellite constellations like Starlink. An external observer would see a planet enveloped in a rapidly growing shell of technology, a telltale sign of a species entering its early spacefaring age. Our electromagnetic signature is a cacophony. For over a century, our radio and television broadcasts have been leaking into space, creating an expanding bubble of noise that now extends over 200 light-years in radius, announcing our presence to any listener within that sphere. Our atmosphere bears the chemical markers of industry: elevated carbon dioxide, methane, and chlorofluorocarbons, technosignatures that a sophisticated observatory like our own James Webb Space Telescope could detect from light years away. We are loud, we are visible, and we are advertising our technological adolescence with all its accompanying brilliance and immaturity. We have split the atom and created weapons that can end civilizations. We have connected the globe via the internet and filled it with misinformation and strife. We have reached the moon and then, for decades, turned our focus inward. An advanced observer would see a species of immense potential and profound contradiction, capable of stunning creativity and shocking self-destructiveness. If Atlas is an artificial probe, it is not just a passive rock we are studying. It is an active sensor that is, in turn, studying us. It is collecting data on our technological level, our social organization, our planetary health, our response to its presence, our global scramble for data, the public speculation, the debates over information suppression, is all part of the dataset. An advanced civilization reviewing this data might conclude that we are not yet a coherent planetary society capable of managing the implications of contact. Our lack of a unified voice, our tendency toward conflict and secrecy, could be seen as markers of a species that is not yet mature. This is why transparency in the study of objects like Atlas is so critical. If we hide data from ourselves, we not only hinder our own science, but we also present a fragmented, deceptive face to the cosmos. The data suppression debate is not just an internal academic squabble. In a scenario where we are being observed, it is a performance of our own dysfunction. The protocols for first contact exist, but they are not binding. And the reality is that a confirmed discovery of extraterrestrial intelligence would trigger global chaos, with governments, media, and scientific institutions pulling in a dozen different directions. We are not prepared. Atlas may not be the catalyst that forces this moment of contact, but it is a dress rehearsal. It forces us to ask, who speaks for Earth? How do we respond? What do we want to project to the universe? The sky has always been a mirror, and now we are realizing that it might be a two-way mirror. We are looking out, but we can no longer assume that nothing is looking back. The final act of the Atlas story is not just about what the object is, but about what its presence reveals about us. As it disappears behind the sun, we are left not only in anticipation of its return, but in a moment of profound self-reflection, a chance to consider what kind of civilization we are, and what kind we aspire to become before the universe takes a closer look. The moment has arrived. As clocks around the world tick past the calculated threshold, 3i Atlas officially crosses the invisible line into solar conjunction. The last data points from ground-based telescopes trickle in, a final, faint photometric measurement from an observatory in Chile, a last astrometric flag from a dedicated amateur in Japan, and then nothing. The cosmic curtain has fallen. The connection is severed. The object is now a ghost, its position and state known only through extrapolation and theory. In observatory control rooms, screens that were once filled with data streams from tracking programs now sit idle or are repurposed for other targets. There is a palpable sense of loss mixed with anticipation, the quiet after the storm of frantic observation. The scientific process now enters a new, more speculative phase, modeling and prediction. Teams of dynamicists and Comet specialists are running sophisticated simulations, creating 1,000 digital versions of Atlas, each with slightly different parameters. They are modeling its thermal evolution, predicting how deeply the solar heat will penetrate its nucleus. They are calculating the stresses of tidal forces, estimating the likelihood of fragmentation. They are projecting its outgassing rates, trying to foresee how its activity might change its velocity and spin. These models are our digital proxies for the object we can no longer see. They are our best guess at what is happening in the silence. But they are only guesses. Every comet has its own personality, its own unique structure and composition that leads to unexpected behaviors. Atlas, as an interstellar object, is the ultimate wild card. Our models are based on comets that formed in our own solar system. Atlas is a product of an entirely different environment, with a history we can only imagine. The simulations, therefore, are not predictions so much as a range of possibilities, a map of what could be happening behind the sun. The most critical date in this digital wait is October 29th, perihelion. In the simulations, this is the moment of peak chaos. The digital Atlas models flare with intense activity. Ices of water, carbon monoxide, and carbon dioxide sublimate violently, creating powerful jets. The simulated nuclei spin up, crack, and in some of the more dramatic model runs, split apart into multiple fragments that drift away from each other along similar orbits. The energy environment is extreme. The solar radiation flux is intense, and the solar wind pressure increases dramatically. For the scientists watching these simulations, it is a frustrating exercise. They are witnessing a climax that may or may not be real. A digital fantasy of what might be occurring 203 million kilometers away, hidden by a ball of incandescent plasma. This period is also when the indirect observational assets become most critical. All eyes are on the data from SOHO and Stereo. The teams operating these spacecraft have programmed them to be especially vigilant, their instruments scanning the regions near the Sun where Atlas should be, looking for any hint of its passage. They are not looking for the nucleus itself, which is too faint, but for its effects. Could its coma, if large and bright enough, create a visible smudge in the coronagraph data? Could its interaction with the solar wind create a detectable perturbation, a ripple in the constant flow of charged particles? The Parker Solar Probe, diving closer to the Sun than any human-made object before, is in a unique position to potentially sample the material Atlas might be ejecting if their paths were to intersect in just the right way. The chances are slim, but they are not zero. This is the long, patient, and uncertain work of the silence window, sifting through indirect data, running simulations, and waiting for a ghost to make its presence known through the faintest of echoes. With the primary object of interest now invisible, the narrative of 3i Atlas fractures and expands, flowing into the broader and more turbulent currents of public and scientific discourse. The story is no longer solely about data. It is about perception, belief, and the very nature of evidence in an age of information overload. In the absence of new observations, the pre-conjunction data is being subjected to a level of scrutiny it never received before. Independent researchers, citizen scientists, and rival academic groups are now downloading the publicly available datasets from the Minor Planet Center and Telescope archives, running their own analyses. They are applying novel algorithms, different reduction techniques, and alternative physical models to the same set of numbers and images, hoping to find something the original teams missed. This is the replicability and scrutiny that is the hallmark of good science. But in the vacuum of conjunction, it takes on a more urgent and sometimes contentious tone. Online forums and social media platforms become the new front lines of the Atlas story. The whispers about anomalous spectroscopy evolve into full-blown theories. Some claim to have analyzed the public data and found evidence of refined metals or unusual isotopic ratios. Others create elaborate videos overlaying Atlas's trajectory with the positions of planets, arguing the path is too perfectly aligned for gravitational assists to be accidental. The phrase, "it's a reconnaissance probe," transitions from a speculative question to a stated fact in certain circles. This is complemented by a surge in historical revisionism. Every past astronomical anomaly is suddenly re-examined for connections. Old, grainy images of unidentified aerial phenomena are presented as evidence of previous visits. The 19th WOW signal is cited as proof that they have been trying to get our attention for decades, and that Atlas is merely the latest and most physical attempt. This public narrative begins to influence the scientific one. Journalists now ask astronomers not just about orbital mechanics, but about the likelihood of Atlas being an alien spacecraft. Funding bodies and university press offices feel the pressure, leading to carefully worded statements that emphasize the overwhelming probability of a natural origin while cautiously acknowledging the intriguing nature of the coincidences. The conversation Avi Loeb started has now escaped the confines of academic journals and has become a global talking point. This period is a case study in how a scientific mystery evolves into a cultural phenomenon. The black box of conjunction becomes a Rorschach test for humanity. Those inclined to trust institutions see a fascinating natural object. Those skeptical of authority see a government cover-up in the making. Techno-optimists see the dawn of a new era of contact. Apocalyptic thinkers see a harbinger of invasion. The true nature of Atlas is now secondary to the stories we tell ourselves about it. The object, silent and hidden, has become a screen onto which we project our deepest hopes, our deepest fears, and our deepest beliefs about our place in the cosmos. As the world speculates, the cutting edge of the search for intelligence is already moving beyond the debate, leveraging the very technologies that define our modern age. The application of advanced artificial intelligence to the Atlas pre-conjunction dataset is underway, and the initial results are both confounding and electrifying. One independent AI research group, using a neural network trained to identify anomalous patterns in complex systems, has flagged a series of minuscule periodic fluctuations in the comet's light curve. The pattern does not match the smooth, predictable brightening of a comet approaching the Sun, nor does it align with a simple rotational model. The AI assigns a high confidence score that the signal is non-stochastic, that is, not random noise. The pattern is complex, a subtle, repeating sequence of dips and rises in brightness that is buried deep within the photometric data. To human analysts reviewing the same data, these fluctuations were dismissed as instrumental noise or the effects of seeing in Earth's atmosphere. The machine, devoid of such preconceptions, sees a pattern. The immediate question is, what could cause such a signal? Natural explanations are proposed. Perhaps it is the signature of a complex precessing rotation, like a wobbly top spinning through space. Perhaps it's caused by the interplay of outgassing jets from multiple points on a highly irregular surface. But the AI's pattern recognition algorithm suggests the sequence has a higher degree of order than typically found in such chaotic natural systems. Meanwhile, a separate analysis, using a different machine learning approach focused on trajectory optimization, has produced another intriguing result. When the AI is tasked with finding the most energy-efficient path for a probe to survey the inner solar system, while minimizing observation from Earth, the resulting simulated trajectory bears a striking resemblance to the actual path of Atlas. The model suggests that a small, precisely timed thrust at perihelion, exactly the moment we cannot observe, could set the object on a new course, perhaps to rendezvous with Jupiter in a few years for a gravity assist, or to alter its exit vector from the solar system toward a specific next target. Again, this is not proof. A natural outgassing event could by pure chance mimic such a maneuver, but the convergence of multiple AI systems, using different data and different models, all pointing toward anomalous, non-random features, is causing a quiet stir within the circles that have access to these preliminary results. This represents a fundamental shift in the methodology of discovery. We are no longer just building bigger telescopes. We are building smarter filters for the data those telescopes collect. The AIs are acting as cognitive extensions, allowing us to perceive patterns and correlations that are simply beyond the resolution of human perception and analysis. The implications are staggering. It suggests that the evidence for or against the artificiality of Atlas might not be a single, spectacular piece of data, but a constellation of subtle, statistically weak signals that only become significant when viewed in aggregate through the lens of a powerful analytical engine. The smoking gun may not be a gun at all, but a faint digital whisper, a ghost in the machine that only another machine can hear. As Atlas continues its hidden journey, the AIs continue their silent, relentless analysis, suggesting that the answer to the mystery may have been hiding in plain sight all along, waiting for a mind capable of seeing it. The silence surrounding Atlas is not merely an absence of light, it is also a potential canvas for other forms of signal, a fact that has triggered one of the most comprehensive and clandestine listening campaigns in the history of SETI. While the public's attention may have drifted, a coordinated, global effort is underway to monitor the conjunction zone for any form of electromagnetic emission that could be linked to the hidden object. Radio telescopes from the Allen Telescope Array in California to the Meerkat Array in South Africa have dedicated precious observing time to stare at the point in space where Atlas is calculated to be. They are not just listening for simple, repetitive pulses. They are employing the latest signal processing techniques, searching for complex modulations, broad-spectrum bursts, or even signals hidden in the noise using advanced compression and encryption algorithms that would be indistinguishable from background static to older systems. The search has expanded beyond radio. Infrared telescopes are monitoring for unusual heat signatures, the waste heat from an active power source, for instance. Optical telescopes are searching for the telltale flash of a laser communication beam, a technology we ourselves are beginning to master for deep space communication. The search is a testament to how seriously the scientific community is taking the possibility, however remote, of a technosignature. The Loeb factor has ensured that the effort is more than just a token gesture. Yet, the results so far are a profound and unsettling silence. No anomalous radio signals, no laser pulses, no unexplained infrared sources. For the skeptics, this is the most compelling evidence yet that Atlas is exactly what it appears to be, a dark, inactive chunk of primordial ice and rock. How could an advanced probe be completely radio silent? They argue It would require power for its systems, and that power would generate detectable waste heat. Any form of active sensor or communication would leave a trace. The utter lack of any such signal is, for them, case closed. The proponents of the artificial hypothesis have a ready and technologically sophisticated counter-argument. They point to our own technological evolution. The most advanced military aircraft on Earth are designed specifically for stealth, to be invisible to radar and to emit as little heat and radio noise as possible. An interstellar probe, built by a civilization potentially millions of years more advanced than ours, would undoubtedly possess stealth technology far beyond our comprehension. It might use passive sensors only, absorbing sunlight and radio waves from our own civilization to power its systems. Its communication might not be a continuous broadcast, but a single, tightly focused, and incredibly brief burst of data aimed not at Earth, but at a relay point in deep space or timed for when its home system is in the right positional alignment. It might use quantum entanglement for communication, a method that leaves no classical electromagnetic trace. The silence, therefore, is not evidence of absence. It could be evidence of sophistication. It is the silence of a predator stalking its prey, or of a reconnaissance drone operating under strict emissions control. This debate highlights the fundamental problem of searching for intelligence. We are looking for something that, by its very nature, may be actively trying to avoid detection, or may be using methods of operation and communication that are as far beyond our current understanding as a smartphone would be to a caveman. The Great Listening Campaign continues, its dishes and sensors pointed at the empty space behind the sun, listening for a signal that may never come, or that may have already come and gone in a form we fail to recognize. While we focus on the object hiding behind our star, a parallel and potentially related discovery is emerging from the study of our star itself. The solar storms that Noah warned about are not just creating terrestrial auroras. They are also having a measurable impact on the sun's own extended atmosphere, the heliosphere. Data from the Parker Solar Probe and the SOHO spacecraft indicate that a recent series of coronal mass ejections has created a temporary, complex structure of shocks and density variations in the solar wind in the region of space where Atlas is traveling. This is not a uniform, smooth flow of particles, but a turbulent, rippling sea of plasma. For a natural comet, this would be a significant environment. The changing pressure and magnetic field strength of the solar wind can compress a comet's ion tail, cause it to disconnect and reform, and even influence the chemistry of the coma by altering the rates of ionization. If Atlas is a typical comet, its activity and appearance when it re-emerges will have been shaped by this solar weather. Its tail might be more disordered, its coma more extended or distorted. However, if Atlas is not a typical comet, its interaction with this turbulent plasma could be different. An artificial object with a potentially non-porous metallic or composite hull would interact with the solar wind in a fundamentally different way than a fragile, icy nucleus. It might not form a traditional ion tail at all. Instead, its passage through the magnetized plasma could create a much more subtle signature. A specific type of plasma wake or a localized disturbance in the magnetic field that our current instruments are not sensitive enough to detect. But that might be inferred from complex modeling. The solar storms add a layer of noise to the system, making it harder to isolate the signal of Atlas's intrinsic behavior. Any strange appearance post-conjunction could be attributed to the extreme space weather it endured, providing a perfect natural explanation for unnatural features. This is the challenge of studying a single unique object. We lack a control. We cannot compare how Atlas handles a solar storm to how a dozen other interstellar objects handle the same storm. We have only this one data point. The solar activity also serves as a reminder of the immense energies involved. The power of a coronal mass ejection dwarfs anything humanity has ever produced. For a probe utilizing the Oberth effect, this turbulent energy is not just an obstacle, it could be a resource. A sophisticated craft might be able to use the magnetic and kinetic energy of the solar wind itself for propulsion or power, riding the stellar fury like a surfer on a wave. As the sun continues its active cycle, it is not just hiding Atlas, it is actively engaging with it, testing it, and shaping the conditions of its passage. The object on the other side of the sun will not be the same one that went in, and the difference will be due not only to its own nature, but to the violent embrace of our star. Disentangling those two factors, what the sun did to Atlas and what Atlas did itself, will be the primary scientific challenge when the silence window finally opens. The implications of the Atlas event are now rippling beyond astronomy and into the halls of power, triggering a quiet but intense discussion at the highest levels of government and international policy. The scenario, long relegated to science fiction and fringe academic papers, is being gamed out in earnest. What is the protocol if an interstellar object is confirmed to be artificial? While the public enjoys the mystery and scientists debate the data, security and policy experts are grappling with a list of unprecedented questions. Who has the authority to speak for Earth if a response is deemed necessary? The United Nations, the world's most powerful nations acting in concert. The scientific community? There is no agreed-upon answer. The existing, non-binding protocols for SETI discovery are suddenly appearing hopelessly inadequate. What are the defense implications? If an object can travel between stars, its technological capabilities are so far beyond our own that any notion of a military response is laughable. Yet, the very presence of such an object in our solar system, especially one that has positioned itself to be unobservable during a key maneuver, is inherently interpreted by strategic minds as a potential threat. It demonstrates a capability for stealth and precision that is deeply disconcerting. This has led to a renewed and highly classified interest in our own planetary defense and space situational awareness capabilities. The ability to track small, fast-moving objects in near real time is no longer just about preventing asteroid impacts. It is now also about monitoring for visitors. There are also urgent discussions about information control. The rumors of withheld spectroscopic data, whether true or not, have highlighted a critical vulnerability. In a crisis of this magnitude, the control of information is power. Governments are acutely aware that the announcement of contact with an extraterrestrial intelligence would cause global, societal, and economic disruption. There would be panic, religious fervor, and a complete reshuffling of global priorities. The decision of when and how to release such information is now being treated as a matter of national and international security. This creates an inherent tension with the scientific principle of open data. The astronomers tracking Atlas are working in a world of publish or perish and open collaboration. The governments funding much of their work are operating in a world of need to know and strategic advantage. The Atlas event, even if it turns out to be entirely natural, is a dry run for this collision of cultures. It is forcing the creation of new, informal channels of communication between scientists and security agencies. It is prompting a review of classification policies for astronomical data. The object hidden behind the sun has become a catalyst, forcing humanity to begin the painful, messy, and necessary process of growing up as a planetary civilization. We are being forced to think as a species, to confront the fact that we are no longer isolated, and to prepare for a universe that is far more crowded and far more mysterious than we ever imagined. As the weeks of the silence window wear on, the initial frenzy gives way to a more profound and philosophical anticipation. The story of Three-Eye Atlas is evolving from a scientific puzzle into a cultural touchstone, a symbol of humanity's relationship with the unknown. Artists are creating works inspired by the hidden visitor, paintings of a dark, enigmatic shape passing behind the fiery disk of the sun, symphonies composed to represent the tension of the silence, poetry that grapples with the scale of interstellar distances and the loneliness of the long-distance traveler. The object has captured the global imagination because it perfectly embodies a fundamental human experience, the agony and the ecstasy of not knowing. We are a species that has filled in the maps of our planet, sequenced our own genome, and peered back to the beginning of time. Yet, here is a mystery, literally hidden in the light of our own sun that we cannot solve. It is a humbling reminder that for all our knowledge, the universe still holds secrets just beyond our grasp. This period of waiting is also a time for reflection on our own cosmic journey. We have our own messengers traveling into the void. The Voyager 1 and 2 probes, now in interstellar space, carry golden records filled with sounds and images from Earth. They are our own primitive version of Atlas, physical artifacts carrying a message to whoever might find them long after our civilization is gone. Thinking of Atlas as someone else's Voyager reframes the encounter. It might not be a hostile invader or a curious scientist, but a silent archaeologist, a relic from a dead civilization on a pre-programmed journey to catalogue the galaxy. This paleontology hypothesis is a sobering thought. First contact may not be with a living civilization, but with its automated post-biological legacy. The probe would be an echo of a culture that may have died out 1,000,000 years ago, its builders never knowing if their message would be received. This makes the act of observation itself a profoundly meaningful almost sacred act. By studying Atlas, we are potentially bearing witness to a civilization that no longer exists, fulfilling the final, long-deferred purpose of its creators. We are becoming the recipients of a message that was sent on a journey of millions of years. This shifts the narrative from one of fear to one of cosmic stewardship. The waiting, therefore, is not an empty interval. It is a period of collective deep breath, a moment for humanity to mature its thoughts and emotions about its place in the cosmos. When Atlas re-emerges, our response will be telling. Will it be one of fear, of weaponizing and paranoia, or will it be one of wonder, of a shared global effort to understand and communicate? The object behind the sun is a test. It is testing our science, our technology, our governments, and our collective spirit. We are being graded on our curiosity, our wisdom, and our courage, and the final exam is just a few weeks away. The focus of the global astronomical community is now shifting from the past to the future, from data collection to preparation for the re-emergence. The moment when Atlas peeks out from behind the sun's glare is calculated to the minute, and it will trigger the most intense and coordinated observational campaign ever mounted for a single celestial object. The challenge is immense. The object will be faint, low on the horizon in the pre-dawn sky and moving fast. Capturing it will require perfect timing, perfect weather, and a global network of telescopes working in concert. Observatories in the right longitudinal band in East Asia and Australia will have the first shot. They are on high alert, their schedules cleared, their instruments calibrated and ready. The game plan is multi-pronged. The first priority is recovery astrometry. The instant the object is detected, its precise position must be measured to answer the most urgent question: has its trajectory changed? Even a tiny deviation from the pre-conjunction orbit could indicate significant non-gravitational forces at work during perihelion. The second priority is photometry and imaging. What does it look like? Is it still a single-point source? Has it brightened dramatically due to new activity? Or has it fragmented, appearing as a fuzzy, extended blob or a string of individual fragments? The third priority, as soon as the object is bright enough, will be spectroscopy. This is the moment of truth for the composition rumors. Astronomers will be comparing the new spectra directly with the pre-conjunction data, looking for any changes in the molecular and atomic lines. Has the outgassing composition changed? Are there new, unfamiliar emission lines? The world's most powerful telescopes, including the James Webb Space Telescope, are scheduled to turn their gaze toward Atlas as soon as it is feasible. JWST's infrared eyes could peer deep into the Comet, analyzing its thermal properties and searching for complex organic molecules in ways impossible from the ground. The re-emergence will be a chaotic, exhilarating, and globally televised scientific event. News networks will have reporters stationed at major observatories. Live streams from amateur astronomers will flood the internet. The hashtag #JohnAtlasReturns will likely trend worldwide. In the midst of this chaos, the scientists must work with cool precision. The first images and data points will be raw and noisy. It will take time to process them, to confirm findings, to avoid the rush to judgment. The world will want answers immediately, but good science requires patience. The tension will be between the slow, meticulous pace of analysis and the frantic, real-time demand of the 24-hour news cycle and social media. The re-emergence of Atlas will not be the end of the story. It will be the beginning of a new and even more intense chapter. The weeks of silence will be over, but the noise of discovery, debate, and revelation will be deafening. Then it happens. From an observatory in Siding Spring, Australia, the first signal, a faint but unmistakable speck of light, appears exactly where the orbital mechanics had predicted, a few degrees above the eastern horizon in the creeping dawn. The email alert flashes across the globe. Atlas recovered. The message is terse, followed by the preliminary coordinates. Within minutes, telescopes in Hawaii, Chile, and the Canary Islands, where night is still holding, swing into action, confirming the detection. The first raw images are released to the public. They are underwhelming to the untrained eye, a single, slightly fuzzy star-like object against a black background. But to the astronomers, the first crucial data is already pouring in. The initial astrometric measurements are processed within the hour. The results are perplexing. The object is not precisely where the pure gravitational model, based on pre-conjunction data, predicted it would be. The deviation is small, measured in arcseconds, but it is statistically significant. Atlas is on a slightly different path. The non-gravitational parameters have changed. Something happened during perihelion that gave it a small but measurable push. The immediate and heated debate begins. Is this the signature of a massive asymmetric outgassing event, a natural jet of gas acting as a rocket, or is it the result of a controlled, engineered maneuver? The early photometry shows that the object has brightened considerably, as expected for a comet after perihelion. But the light curve is strange. It doesn't show the smooth, steady decline of a comet settling down after its close encounter. It flickers. It has a non-periodic variability that is complex and hard to model. The early low-resolution spectra are obtained. They confirm the presence of common cometary volatiles water, CO, CO2, but the ratios are different. The water vapor signature is weaker relative to the other gases than it was before conjunction. It's as if the object has lost a layer of surface water ice, revealing a different composition beneath, or, as some are already whispering, as if it vented something other than ice. The imaging data is scrutinized pixel by pixel. Is it a single point? The initial analysis suggests it is, but there are hints, just at the edge of resolution, of a faint asymmetric extension. A dust trail? A small, separated fragment? It's too soon to tell. The first 24 hours post-recovery are a whirlwind of contradictory data, rushed analyses, and rampant speculation. The scientific community is divided into camps. The naturalist camp points to the trajectory change as clear evidence of a strong natural outgassing event. The changed spectrum and light curve are, to them, proof of the violent thermal processing the object underwent. The anomalous camp, bolstered by the AI findings from the pre-conjunction data, sees the precise nature of the trajectory change, the complex light curve, and the altered composition as red flags that cannot be easily explained by standard comet models. The truth is, no one knows. The data is still too raw. The object is still too close to the sun for optimal observation. The story of Atlas is no longer about its disappearance, but about its return. And the returned object is not the one we said goodbye to. It is changed. It is different. And figuring out why will consume astronomy for years to come. The reappearance of 3I Atlas marks not an end, but a profound and permanent beginning. The object, now steadily pulling away from the sun and fading as it heads back into the interstellar dark, has left an indelible mark on our science, our culture, and our species' self-conception. The intensive post-recovery analysis will continue for months, yielding dozens of scientific papers arguing for every possible interpretation of the data. The official, consensus view will likely settle on a natural origin with unusual characteristics, a convenient and scientifically safe conclusion that acknowledges the anomalies without requiring a paradigm shift. But the seed of doubt and of wonder has been planted. The Atlas event has proven that interstellar objects are not merely theoretical curiosities. They are real. They are visiting with a frequency we are only beginning to detect, and they can behave in ways that challenge our textbooks. It has validated the need for projects like the Vera C. Rubin Observatory, which will find many more of these visitors, allowing us to move from the study of singular anomalies to the understanding of a population. The Sagittarius Corridor hypothesis will be debated and modeled, becoming a legitimate, if unproven, area of astrophysical research. The event has also changed the players. Avi Loeb's Galileo project will receive a surge of funding and support. Its mission to systematically search for techno-signatures, now seen as less fringe and more prescient. Government space agencies will quietly increase budgets for planetary defense and deep space tracking, with a new, dual-purpose focus. The conversation about humanity's place in the cosmos has been irrevocably altered. We can no longer look at the night sky as a passive tapestry of lights. We must now see it as a dynamic and potentially active environment. Every faint moving dot could be a rock, or it could be a messenger. The distinction is now a matter of empirical investigation, not philosophy. Atlas itself is now gone, a receding speck on a hyperbolic trajectory out of our solar system, never to return. It came, it saw, it did something, and it left. We were given a front row seat to an interstellar event, but the main act was hidden from our view. We are left with the echoes, the data, the questions, and the haunting, unshakable feeling that we are not alone, and that we have only just begun to learn how to see our neighbors. The universe has spoken. It has given us a mystery. Our long apprenticeship is over. The real work is just beginning.